Hello again. This is Math 2231 Remote Delivery for April 21st, 2020, and this is Use Substitution Part 2. Do not cheat yourself by moving directly to the answer, but spend a little bit of time working on the problems in order to perfect your understanding. I'm leading off with a little bit of insight from the Part 1. How do you know if magic happens? Well, the most important thing to remember in substitution problems is that after the substitution, all original variables need to disappear, vanish. That's how come I call it magic, from the integral. After the substitution, the only variables that should be present are the new variables, usually u. And note, and this is very important, that includes the variables in the differentials as well. That's why we solve for the original variable like dx or whatever it is. So that was really the takeaway from last time, but you want to take that with you because that is an important thing. The takeaway from this one is that there are many integrals that on the surface look very similar, but yet will use a completely different solution or will yield a completely different answer when using the same substitutions. That'll make more sense after we talk about the examples. So here are your first 4 examples. I strongly recommend that you pause the video, try to do all of these before you return, and that will make you more primed to understand the solutions. So pause now and we'll see how you do. Here's the problem that we were trying to do right here, and so the solution that's going to work is u equal 5y plus 4. That means that du is equal to 5 dy, and that means that dy is equal to 1 over 5 du. If we make all of those substitutions, we can factor out the 3 over 5, and we're integrating 1 over u du, which is the ln of the absolute value of u. And again, the constant, we just let it fly. This is maybe a different constant because you're having 3 over 5 times it. And then we have to substitute back into the original variable to have this as our final answer. In the second problem, this is the one we were trying to solve. So the substitution that will work this time is u equal 5y squared plus 4. Now that means that du is equal to 10y dy, and solving for dy, that means that dy is equal to du over 10y. So if we make those substitutions for the dy and for all of this, magic happens because the y cancels, and we have 3 over 10. This is the integral of 1 over u du. That again is the ln of absolute value of u, and this is our final answer to that problem. Here's the next problem that we're doing, and again all of these are slightly different. Here we have a power in the denominator. The same substitution will work that we used in the last one, but notice that now we don't have 1 over u, we have a different form, so the answer is going to be different. So we add 1 to the exponent and divide by the new exponent. Notice that a minus sign pops up, and we have this as the answer in terms of u, and this is the answer in terms of y, and it could have been written this way, or if perhaps you wanted to write it this way without a negative exponent. This one is a little bit different. You had to recognize the pattern. You had to recall that the derivative of the arctangent of u is 1 over 1 plus u squared du dx. So that means the integral form of that is the indefinite integral of 1 over 1 plus u squared du is equal to the arctangent of u plus c. Now this is the problem that we're being confronted with, and you have to say, wow, I need to make that denominator look like 1 plus u. And so here are ways to do it. You can factor out the 4, and then you can move the 3 over 4 through the integral. You have this expression. And then we have to just say, oh, well, we'll make this u squared, and here is the answer that if I square this expression, I get 5y squared over 4. So that's the substitution we're going to use. So u is going to be equal to that. Du is going to be the square root of 5 over 2, and that is now just dy. So dy, solving for it, is this. So then we make all of those substitutions, so we find the integral that we were trying to compute to start with is equal to 3 over 2 the square root of 5. That is the exact number that gets factored out. And this is an integral of 1 over u squared plus 1 du. That is the inverse tangent or arctangent of u. And then our answer must be in terms of the original variables for it to be correct. And so this is the expression that we get for the answer to that problem. 4 more problems for you to do. Again, I strongly recommend for your understanding that you pause the video, try to do these yourself. Maybe you'll surprise yourself and really do well on these. Maybe you'll learn something, but you'll, in any event, be better prepared to understand the solutions when we go over them. So pause the video now. Let's see how you did. Well, this is the first problem that we were embracing. And so the substitution we're going to do is u is equal to t to the 4th plus 2t. Now when I take the derivative of this, I will find that du is equal to 4t cubed plus 2. And it's convenient to factor the 2 out, because that way it is clear that magic is happening, because this is in the numerator over here. So then we solve for dt, and we get this. Then we substitute everything in. So we'll find out that the 1 over 2 factors through the integral, and we have 1 over u cubed du. Now that is u to the minus 3. And so I add 1 to the exponent, divide by the new exponent, I get this expression. And then I substitute back in terms of the original variables, and I have this as my final answer. This was the problem we were trying to do. And again, we're going to use exactly the same substitution. And we factor out this. But this time we get 1 over u du. And the integral of this is known to be the logarithm of the absolute value of u plus c. I substitute back in terms of the original variables, and this is my answer. Notice the absolute value is important because depending on what t is, this actually could be negative. Here is the problem we were confronted with to start with, and here's a substitution that will make magic happen. U is equal to 1 minus 4x squared. That means that du is equal to minus 8x dx. We solve for dx, and we substitute back into the problem. Again, magic happens because this x cancels with that x, and we're left with this integral upon the substitution is, I factor the constants out, as minus 1 over 8. That is the integral of u to the minus 1/2. Add 1 to the exponent and divide by the new exponent. I get this. And writing it in terms of my original variables, which are the requirements of the problem, I get this. Here was the problem that we were trying to do, and this problem again requires you to remember that whenever we differentiated the arc sine of u, we got 1 over the square root of 1 minus u squared times du dx. So that means that the antiderivative, or the indefinite integral of 1 over the square root of 1 minus u squared du is going to be equal to the arc sine of u plus c. Again, it's important to remember all of these formulas. So that means we need to make this expression look like this expression, and that motivates the substitution of letting u be 2x. Let's do that. So if u is 2x, du is 2 dx, and dx is 1/2 of du. And that means our original integral then becomes this. I pull the 1/2 out of the integral, and I'm integrating this form. That is the inverse sine of u plus c. And then I substitute back in terms of the original variable, which is a requirement for solving this problem. This is the end of part 2. See you in